Welcome, guys. Today we got entry 2. We're going to talk about molarity and other forms of concentration. We're going to review solutions a little bit first, though. Just a couple things that we talked about last week and connect it to our new topic this week. So, first one, review what is concentration. It's a ratio of our solute to our solvent or total volume of solution. Okay, so here, notice you have a certain amount of solute, you have a certain amount of solvent. When I mix them, the volume goes up. So the ratio would actually be the amount of that solute to the total volume at the end. Okay, so usually the solute we measure in a mass in a lab, but the idea here is moles. So the almighty mole comes back again. And then volume will be in liters. So remember, when we're dissolving, our solute or our solid goes in, and then the water molecules tend to pull it apart if it's a solid, or separate them in more of a liquid-liquid mixture here. And that process just takes time, and stirring and other ways you can change the rate that that dissolving occurs. Okay, second piece is what is a solution? So remember, solutions are a homogeneous or evenly spaced mixture of two or more substances. It has two major groupings. We have the minor ingredient, the particles, that's your solute, and the solvent, which is going to be water for us, that's the major ingredient. But if I had two gases, the one that you have more of would be your solvent, the one you have less of would be your solute, and so forth. Solids would be like metal alloys and things of that nature. So there's your solute and solvent. You're not able to really see those things. So remember, up to this point, we're assuming that all things are mixing, but when we have two different polarities, they don't mix, but if the polarities are the same, then it will mix, and that's because water in itself is a polar molecule. So if I have ionic salt, so just a salt and water, it will dissolve, and if I have because they both have like positive and negative ends, and if I have oil and water, the oil, which is non-polar, and the water, which is polar, separate out and they do not mix. Lastly, what impacts solubility? We got temperature, pressure, and solute. The more solute they have, the less likely it is to dissolve. There's only so much the solvent can dissolve, and temperature higher is better. Higher temp is better solubility. That's because there's more energy. So you can see that here, which one is warm water? The one where it's spreading out faster. There's more energy here. The particles are moving faster, so you get better solubility than the cold glass of water over here. So there's many ways that we can measure concentration of our solutions. We're going to focus mostly on molarity, but I want to go over these other ones with some real life examples. So where would I see parts per million, parts per billion, percent by mass, and percent by volume? So percent by mass, an example of that would be your daily value of nutrients. So if I look at a nutrition label, there's 3.5 grams of fat per serving. That's 5% of your daily value, meaning if I knew the total number of grams of fat I needed, they're assuming based off a standard 2,000 calorie diet, that I'm taking in 65 grams. So 3.5 divided by 60 is going to give me 5, and so forth. For our carbohydrates, 9 grams, 9 divided by carbohydrate, 300 would give me my percent 3. Protein, 1, it's not given, but normally most people are eating somewhere around 80 to 100 grams of protein a day, depending on your fitness goals. Examples of percent by volume. These are tons of daily items. So like if I had hand sanitizer, it's 62%, and that VV means 62% of it is ethyl alcohol. The other percentage is something else, some mixture of these inactive ingredients. Isopropyl alcohol, we got 70%. That means 70% is the actual isopropyl alcohol molecule, and the other 30% is water. Vinegar, other medicines, and things of that nature often are expressed in either percent by mass or percent by volume as well. So you see this in grocery stores and all that very often. Parts per million, an example, sorry, this one is a little out of order. Parts per million down here, that's how they measure the amount of CO2 in the atmosphere. So in this graph, which is taken from NASA, you can see from the 60s to today, the amount of CO2 in the atmosphere has gone up, and it's measured in parts per million. Out of the 1 million air particles, 400 of them are CO2, and that amount obviously goes up and down. Parts per billion, that's a way you can reflect concentration of a solute. One example of that would be if you read this article that was attached in the toxicity lesson, the lead in Flint, Michigan, in their water sample, that would be one way. So basically, if there's 5 parts per billion out of a billion particles, if 5 of them are lead, that's something that we need to do something about, or at least be concerned about. If it's 15 or above, 15 parts per billion, that would be something that is actionable, meaning you have to do something about it. See, Flint was average 27 parts per billion, but the highest level was 13,000. So you can imagine that if you're consuming that 13,000 particles out of a billion, was going to give you a much higher threshold than that 5 to 15 range that is actionable. So a molarity, though, is really, and this is something that was in your notes before, it's moles of solute over liters. But this is the new idea. This triangle should be on your note sheet, but make sure you take this down and you understand what each of these things is. So molarity is equal to moles divided by liters. So let's just look at some example problems. And again, if you need to pause here, go for it. I just ran through stuff pretty quick, but if you have questions, let's go for it. So the first example, what is the molarity? That means concentration. What is the concentration of a solution if there's 2 moles in 4 liters? So remember with these triangles, if I just cover it up, so I imagine I put my cursor here over molarity, that tells me I need moles divided by liters. And then I can just plug in my information. So molarity is moles divided by liters. I got 2 moles, 4 liters. I get 0.5 molar potassium nitrate. So that's how you'd say it, 0.5 molar. Molar is how you would say it. That's the label like liters or grams. So this next one says how many moles of solute are in 0.4 liters of 2 molar potassium nitrate. So moles right here covered up. That means it's molarity times liters, and then I just plug in my information. And again, if you need to pause to write down everything, that's fine. So moles is molarity times liters. I got 2 molar. I got 0.4 liters. I multiply those out. I get 0.8 moles of potassium nitrate. Next is volume. Volume is liters. So that's moles divided by molarity. So I plug in 5 divided by 2. It gives me 2.5 liters of solution. And the last one, number 4, this is the hardest type of problem because it says molarity. Okay, so I know molarity is moles divided by liters, right? But it gives me grams and liters. So remember, in a lab setting, we would be measuring things in grams, and then at this point, hopefully we know how to convert to moles, which if I start with grams, I'd put grams on bottom, which means I have to divide by the molar mass. So since we have grams, we have to divide by molar mass to get moles. So 20 grams of potassium nitrate divided by the molar mass, 101, gives me 0.20 when I round. Now I have moles. Now I have liters. So I can just plug them in. 0.20 moles divided by 4 liters gives me 0.05 molar potassium nitrate. Now the next 4 problems should follow the same order, styled exactly after these, so you have one of each of them. So for our quiz on Friday, you can imagine you might have one of each of them, plus maybe some general questions about solutions and other forms of concentration as well. Okay, so let's look at the last 4 problems here. What I'd like you to do is pause and actually try these right now. Okay, pause and actually try them. The math isn't super tough, but when I walk through, I'd like you to actually pause give them a shot, and then you can always come back and look at the key or ask me questions or watch the walkthrough. Molarity is 4.6 moles, 2.4 liters. Moles divided by liters is going to give me 1.92 molar. Next one is moles. Cover up moles. It's molarity times liters, so I multiply them to get 20 moles. Wood volume in liters, so I cover that up as moles divided by molarity. So 3 divided by 12 is going to be 0.25. And lastly, number 4, since I have grams, I'm going to have to divide by the molar mass to give me 2 moles. 2 moles divided by 10 liters. Then to find molarity is going to give me 0.2 molar sodium carbonate. And this is probably the most complicated thing that we'll see this unit. So super cool that it is a little bit simpler than our predicting product stuff. All right, guys, love you, miss you. Have a great day. Let me know if you have any questions.